Yeah, good morning to everyone. I am Chirag Mistry. I am based in Sydney. And this presentation, I wanted to talk about digital substations, some of the learnings that we have made, and some of the design considerations. So, as you know that uh, the concept of digital substation, IEC 61850 station bus, process bus, it's not exactly new, right? We have been talking about it for quite some time. We have had our digital substation pilots back in, more than 15 years back. So since then, we have implemented so many substations. As GE, we have more than 100 substations, either at the pilot stage or real substations, but much more than 100 substations that we have had experience with. And in this presentation, what I wanted to convey is that the question is not whether digital substations or process bus work. So we have moved beyond that. So yes, definitely the technology works very well. We have had plenty of experience. We have digital substations in Indonesia. PLN have built a couple of substations. The question now is what learnings we have made from various implementations we have done, and how well are we using the process bus, how well are we using the digital substations, right? Are we taking the advantages in a way that it provides advantages? So these are the questions that I wanted to focus in this presentation. Okay, so my typical agenda would be to reiterate why digital substations, why do we use it, right? So one approach is that you replace your conventional substation with digital, but we do exactly the same thing what we did in conventional substation. We replicate in digital, but does it give you necessary advantages? So that's something we need to consider. I will talk about different architectures, right? I will talk about design considerations, and we'll see how it goes. It's quite a long presentation, but I'll try to focus on some of the key points. Okay, so number one question, why digital substation, right? So basically, what we are trying to do at the core is we convert the data. So that's the basic thing we do, right? So we have all the data. We have circuit breaker status, we have currents, voltage, and so on. So we try to digitize at the source. So we are trying to digitize in the substation switchyard, right? At the source. The second thing, what we do is we share the data. So number one, we digitize the data. Number two, we share the data between devices at each level and between levels. So between station and process bus level, between station and control center, whatever. So once you have the data available, you can share it freely, right? And the third thing is that we process the data. So we analyze the data at each level, okay? So these are three basic functions in digital substation: convert, share, and analyze. Right. Basically, four reasons for using process bus. So one is execute faster, right? So if you are building a digital substation which involves process bus, you should be able to execute faster. If you are spending the same time as your conventional substation, probably you are not taking advantage of digital substation that it's capable to provide. So you can execute faster, you can reduce the design documentation. From the projects we have experienced so far, the customers are able to reduce the design drawings by about 90%. So previously in conventional substation, you used to produce 100 drawings. Now you are producing only 10 drawings. So design documentation has significantly reduced. Um, you can reduce installation time, commissioning time, you can modularize, you can make design modules and use it like that. Use less, okay? So less use of infrastructure, so less wiring, use less cable trench. Obviously, instead of copper cables, you are using cable trench with fiber optics, so you can reduce that. Smaller buildings, smaller yards, as I'll come to later, operate better, okay? So monitoring is better because now we are dealing with data. So there are sample value signals, there are goose signals, etc. So this data, it's very easy to monitor the data. And if you are able to monitor the data, there is no need for testing. So the testing requirement in digital substation is very limited. It's much better for maintenance. So very few outages, I mean very few maintenance trips, outages, life cycle management. So it all becomes very easy. And basically you unlock the value. So there is a lot of value in the data, as you know very well. And now in the theme of energy transition. So energy transition, one of the building block is that you get the data and you utilize the data properly. So you unlock the value of the data. So first step is the digital substation and getting the data. And then you can build all the application that use the data. Okay, the business goal, right? So what would PLN expect from implementation? So one is the field wiring. Of course, when you remove the field wiring, because each termination need to be tested, you need to spend time to test each termination. So all that requires a lot of time. You can reduce life cycle management, simplified testing. So process bus can eliminate most of the routine testing, okay? And I will show in later slide that some of the features of addition 2 help with the testing. Simplified expansion. If you want to expand your substation, it's quite easy. In a conventional substation, there is a lot of wiring involved. If you install new base, then you need to have new CT, VT signals, new cabling. You need to wire all those interfaces. For example, if you want to expand your busbar protection, you need to add new signals, you need to completely test. And if you completely test the busbar protection, probably you need to have substation outage, right? So those things are very complicated. Digital substations simplify all those things, right? So basically how you execute, right? So basically pick a typical wiring architecture, and there are a number of options, right? If you think about outdoor wiring, the wiring in the outdoor cubicle, one option is that you have remote interface unit, remote IO unit for each device. So for each disconnector, for each circuit breaker, you have separate remote IO unit. For analog interface, for CT, PT, you have merging unit. So this is one approach. So that minimizes the copper cabling. Every IO device has dedicated fiber optic. So this is one such example. Another option is that you use the centralized remote input output unit, centralized RIO, so which manages all the trippings, status acquisition for all disconnectors and circuit breakers in a bay, okay? And you use merging unit for CT and VT. This is another alternative. In this alternative, you have copper wiring in the field from your primary device up to marshalling kiosk, but the rest of things are all fiber optic. The third alternative is that you use the process interface unit. So that's PIU. And PIU is CTs, VTs, status, control, tripping, everything in one device, right? So you can use PIU or in conjunction with remote input output. So it's really your choice what type of wiring you want to pick, but you pick one architecture for wiring, and then wire every identical device the same way, right? So once you have decided that this is what I want to do, I want to use process interface unit, so repeat that for each bay, each identical device. So that means your wiring is standardized. When you produce your outdoor panel, every outdoor panel can be the same, because you know that you are using this process interface unit to connect to the circuit breaker, and all the wiring, all the references could be same, okay? For every identical bay, then your scheme is same, your wirings is same. So now you can imagine that if you apply this to a substation, your drawings, your AC and DC drawings are considerably reduced, right? And it's standardized. When the maintenance guy, when your operator goes to substation, he knows exactly what the wiring is, because he doesn't need to probably refer to the drawing, because he knows that everything is identical. So that's how you can bring the standardization, right? Similarly, for the network design can be standardized, and the same sort of network connection to switches can be applied in a substation, right? So network design can be standardized. The way you filter out your goose messages and sample values, the data traffic, it can be standardized. Build around pre-tested sub-assemblies, right? Okay. So when you have outdoor kiosk or the panel with merging unit or process interface unit, it can be pre-tested in a factory. So when it comes completely tested in a factory, you don't need to spend a lot of time in commissioning at site, right? Simple panels, because now the panels, they don't have much wiring. They don't have wiring at all. This panel has only power supply and fiber optic. So what is there to test? Really nothing, right? So panels can be simple. And pre-tested structures. So this is what some customers do, that they have a plug-in control house. So for example, in a brownfield substation, when you want to refurbish the secondary system in a substation, what they do is that they build this control house, the control building, and they commission that control building as a whole while the substation is running. So during refurbishment, they just drop in the control building in a substation, connect all their fiber optic network, and the building is ready. And as and when you want to cut over all the feeders, okay, from the conventional system to digital, it can be done very, very quickly, okay? And this control building is all pre-tested. So you don't need to perform any test on the site. Of course, you will perform few basic tests, but it's not like a full-fledged commissioning test. It's all commission tested in your laboratory. Right, and commission the entire protection control system during FAT. So during FAT, so now what's the difference between FAT and SAT? Very minimal, right? Because now what we are doing is that we have extensive FAT, then when the equipment goes to site, we conduct very elaborate site acceptance test and spend a lot of time, but ideally we should be able to reduce that time. Okay, so engineering optimization, steel work foundation, if you use optical CTs, VTs, of course you can reduce that. Building foundations, cubicles, they can be considerably smaller because you have nothing but power supply and fiber optic. So you can accommodate many relays in one panel because the relays are smaller. So why do we need to have big number of panels as we have in conventional substation. You don't need cables, ducts, everything can be reduced. So we can say 80 to 90% reduction in copper cabling, which is a big advantage. 80 to 90% reduction in building size, that's possible because your panels are small, no copper cabling. 25% reduction in footprint for some designs. And if you, all this should translate in money, right? You can save a lot of money. And this is what we have witnessed in so many projects. Okay, so first step, save on capital expenditure, and it can be done now. So when you implement digital substation, you straight away save on capital expenditure. And the biggest advantage comes afterwards. So once your substation is built, all the savings that you make during the lifetime of the substation, that's quite significant. Now imagine that once you install your protection control relay, you need to replace it after 15 years or 20 years, right, after the lifetime of the relay. How easy it is to replace conventional relay with all the CTPT wiring, with all the inputs, outputs. It's difficult, right? Because you need to remove all the wiring, you need to reconnect all the different wiring. Your device will be different than previous one, right? So you need to consider the form factor, the wiring shape, everything. Now imagine that when you replace the digital relay with process bus, all you need to do, bring another relay and just shift the fiber optic, nothing else. So that gives you tremendous advantage. Now I'll give you an example of UK power system. So in UK power system, they have lot of renewable sources, okay, lots and lots of wind farms, okay. Now their transmission network is not capable to carry all that power that the wind turbine produces, right? Now the substations, they need maintenance, okay. When the substations need maintenance, they need to take shutdown. When they need to take shutdown, they need to switch off that transmission line for, let's say, 8 hours or 1 day. When the transmission line is switched off, your capacity to carry that power becomes less, right? When the network is not capable to carry that enough power that the wind farm is producing, the system operator needs to pay huge money to wind turbine operator, to wind farms. And that money is really huge. It costs them billions of pounds, billions, right? With digital substation technology, if you want to go for maintenance, if you want to go for relay replacement, instead of couple of hours, you can do this in couple of minutes. This is a big advantage. So you can reduce your shutdown time from a day to an hour, and that will save a lot of money. This is just one example. So there are plenty of things that can be thought about. Process bus gives you separation between primary and secondary, so you have everything that you deal with is data. It's safer data sharing, future-proof digital architecture. So now that you have separated your primary equipment from the secondary system, and all you have done is conversion from electrical quantities to ones and zeros. Now ones and zeros can be dealt with. So tomorrow when your technology moves ahead, your basic information is available and you can use that anytime. So you can quickly update, replace devices and applications, right? So now we are seeing that with renewable integration, there are new applications that are required. The current protection principles, for example, distance relays, they may not be able to cope with the kind of currents and voltages we are seeing in the network. So maybe it needs new applications, right? Maybe it will need new form of protection. But with this approach, your basic infrastructure is ready. So you can very easily adapt to evolving situation. Yeah, and it has complete influence on everything that you do as a business. So from protection engineering to substation design to equipment standards, construction, testing, maintenance, everything. So it will impact total enterprise. The total business will be impacted. And from our experience, from various projects that we have noticed, the key success factor. So you, as a business, you have decided that, hey, let's build digital substation and see how it goes. So what makes it successful, right? Number one, as I mentioned, that the technology works. You build digital substation, it will work, no problem. But the main question is, are you getting enough advantages? That you can do when you maybe standardize. So these are some of the factors that contributes to your success. And this is one of the things is modular design, standard design, off-site construction, pre-commissioning activities that run in parallel to civil and primary. So if you, with this approach, you can reduce your time and money on commissioning activities, collaborative design process, okay, be flexible. So this is one more factor we have noticed in for a couple of utilities, that they had their existing practices, right? So we have our design, we have our secondary design, but when they moved to digital substation, they were flexible, that we are ready to consider changes, right? So this is what we did for conventional station, but for digital, okay, we are flexible, we are open to implementing new changes, right? So flexibility is one of, be open to learn, yeah. So this is one good factor. Embrace opportunities. So look for opportunities where you can save money. For example, you can accommodate 4 feeders in a single panel. Why not do it? Why do we need to have 1 panel per bay? May not be necessary. So look for these opportunities and try to take advantage as much as you can. Organizational and vendor support. So vendors such as GE, whichever vendor you use in your system, vendor support is very critical, because we know, we have a lot of experience from all the implementations that we have made. So like in Australia, we know that couple of customers, when they moved from conventional to digital, the research time or the time to test in their laboratory, it was more than 1 year. So during 1 year, we had extensive collaboration between us and customer. So we also learned a lot as vendor. They also learned a lot. So it was mutually advantageous for both of us. Now, architecture. So a couple of points on implementation. So there could be different types of architecture. So one is separate station and process bus. So here there are different variants. Okay, so one example is you have your station. Now, before we move to station and process bus, in 61850 standard, there is no definition, strict definition for station and process bus. It is for our convenience that we say that process bus is whatever you have in your switch yard, and station bus is whatever you have in your station, substation, right? But technically, there is no difference. Okay. Now, you have your process interface unit, merging units, and you have your IEDs, and this process bus carries all sample values and goes message. In the other variant, what you have is PIUs. They have only sample values here, and goose message, trippings, etc. done by remote I/O unit. So basically, your station bus is extended to the switch yard. Okay, so that's one more variant. Okay, and yeah, if you look at the real architecture, so we have these relays that have separate station and process bus. So this is how it will look in reality in a substation. So both process and station bus are synchronized through GPS clocks independently. So that's one variant. Second variant is separate station and process bus, but here for system A and system B you have complete separation. In previous example you have your X and Y protection, they were in the same network. Here we have used different network. Okay, so this is different variant of that. You can also have one combined network. So in one combined network everything is connected to same set of switches. Okay, very simple architecture. Now this can also be done. So we have all our relays and MUs and BCUs, they are all connected in the same network. Or you can have you can possibly have a separation between station and process bus, but we can have one connection between station and process bus just for monitoring purpose, right? Because you need to access your process devices through HMI. So you need to monitor their health, you need to pass some goose messages from station to process. So you can also have one link between process and station bus. Right, so that's one common network. One combined network with separation between set A and set B. Okay, so that can be done as well. You can think about HSR. So in some countries they have preference for HSR. Okay, so you can have process bus HSR ring per bay, and then you make connection between different rings. HSR architecture generally is very complicated. It's not easy to manage. So for the ease of configuration, engineering, maintenance, PRP is a preferred architecture over HSR. HSR also has advantages, but it's difficult to maintain that. Okay, now there are a couple of advantages and challenges when you think about separation between station and process bus. So if you have a combined station and process, what will happen? Some of the challenges is traffic regulation. Okay, because all your messages are in the same network. So if you don't separate the traffic, all the devices will see all the traffic and it will collapse, right? Because you can see that the Ethernet ports of equipment, they are rated to see some traffic. So typically the IED ports are 100 Mbps. Okay, and if you expose them to sample values, they will very soon it will saturate and it will collapse, so it will stop functioning. So you need to separate the traffic. This is one challenge. If you don't segregate your traffic, your goose performance can suffer. So your goose messages can become slow. Okay, so these challenges can be addressed by good engineering. So you need to have good engineering, right? But the advantage, very good advantage it gives, is that there is a single point for monitoring all the signals, because everything is available in the network. So from any part you can monitor anything. So that becomes very easy for, let's say, HMI applications for monitoring. And reduction in number of switches. So you can reduce number of switches. For separate station and process bus, the challenge is remote monitoring of process bus equipment. So if you want to monitor merging unit from HMI, it's a challenge, right? So in that case, you need to use the relay, you need to use the IED as a proxy to monitor merging unit. So merging unit should be able to send the health data to relay, and from relay you can monitor the health in HMI. So that can be done, but it's bit convoluted process. But the advantage is that there is a clear segregation. Okay, so even if you don't segregate your traffic very well, you can still get away with that. It can be an advantage when different groups, like SCADA group is responsible for station level, protection group is responsible for switchyard equipment, so they can access their own switches, like protection people can access their own switches. So maybe segregation in responsibility and ownership. Easier for refurbishment. So if your existing substation has already a station bus, maybe this can be an advantage. But my point here is that both architectures have their own advantages. If you go for combined architecture, or a combined architecture, or even separate architecture with at least one link between station and process, you can monitor the process equipment quite easily. So your maintenance, your monitoring can be much easier, right? Ring versus star network. As I mentioned that our preference is to, like ring network, you can have RSTP ring or you can have RSTP star, and both have their challenges and their advantages, right? Star network, if the root switch fails, then it takes down the network. If you have ring, then you have some resilience in the network. So there are different architectures at the switch level as well. Right. So this is one example from Transgrid in Australia. So they have used a star network with, and it was very efficient network actually. So they have switch aggregation, right? But they have separated protection or system X and system Y. So anything that happens in system X, system Y is anyway there. So they were not much worried about failure of one particular switch, because you have redundancies always. How much time do I have? Okay. PRP versus HSR, I don't want to tell you every point, but the main thing about HSR is that when you adopt HSR architecture, all your devices have to support HSR. Whereas PRP, you can bring in different equipment, so interoperability, expandability, all that is no problem. But HSR maintenance, if you take one equipment into maintenance, your ring is broken, right? So your redundancy is gone. So all those things we need to consider very carefully. So for big substations, for transmission level substations, PRP will give a lot of advantages. Now, design considerations. Some of the things that we learned through different experiences is that you need to be careful about PTP distribution, because for process bus, time synchronization is very, very important. So you need to pay very particular attention on the PTP distribution and how well the time synchronization works in your substation. Selection of equipment appropriate for process bus operation. So obviously your switches should be able to support PTP. should be able to support PRP in a way that it should support jumbo packets and all of that. Protecting key equipment from network flooding, like GPS clock, merging unit. So as I mentioned in the previous section on the traffic segregation, that if you don't segregate your traffic, some of your equipment will fail straight away. And we have seen these problems many times. So you forget to filter out some VLANs, your GPS will see sample values and straight away it will fail, and it will fail everything else, right? So one simple problem, it will take down everything. So network engineering is very important here. Right. Yeah, effectiveness of redundant GPS clock. So we need to have redundancy in GPS clock. In one of the project I have seen, they have used GPS clock and non-GPS clock in the same design. The reason was they thought that GPS, they have antenna outside of the substation, right? And their thinking was that when there is a lightning event, so GPS antenna is a way to attract, outside influence. So they wanted to make that system resilient. So one GPS clock with antenna and one non-GPS clock without antenna. So that will be the second GPS in the substation, just to make sure that there is no external connection to outside world. So different approaches. Now this was the other. So we had PRP architecture. So here how we have used, so obviously you need to have redundant GPS clock. You just cannot rely on one clock, because if one clock fails, everything else fails. We can't afford that, right? Now when you have two GPS clock, how should you connect? Where should you connect? So this is just one example. Here we have connected 2 ports here and 2 ports at the opposite end in network B. So effectively what it does is that when you have PTP, and if your network is very big, so in some of the substation I have seen that the switch network, it has about 20 switches, right? 20-25 switches. For PTP, if you want to maintain accuracy of 1 microsecond, the message should not travel more than 16 switches, because every switch you have loss of accuracy, right? So here what we have done is that you have one connection here and one connection at the opposite end. So any switch fails, you have or any clock fails, you have alternate message available at one of the ends. So that means in any contingency, your PTP message will not need to travel more than 16 hops. So that's just one design we did. Okay, and yeah, some of the improvements. So this is how we monitor the MU health at HMI when it is not connected to station bus. So this was one example. So at HMI level, you can see that we can monitor different logical nodes and how we display in HMI. So all that time sync fail or single device link failure, so all those things we can monitor in HMI, but it needs additional engineering. Right, then some of the possibilities, right? So we can do some innovative things. 10 minutes, good. All right, in your design, if you have, let's say, main 1, main 2, completely duplicate, so distance 1, distance 2, and these 2 relays are connected to 2 different merging units, okay? So the principle is that if you have failure of one merging unit, you have the second set. So if system A fails, you have system B as an alternative. That's fine. What if you are using main and backup protection? So if you don't have duplicate protection in as a system A, system B, or X and Y, if you have main and backup, so some designs, they have distance as a main protection function, and let's say overcurrent or directional overcurrent as a backup protection function. And the main function is connected to one MU, the backup function is connected to different MU. If you have failure of one merging unit, what will happen is that your distance protection will stop working. Of course, you have your backup function, but distance and directional overcurrent, they are different, right? What we can do is that we have cross-checking feature in UR relay, for example. So we can connect both the sample values to the same relay. So if you lose one MU, you can use the sample value from the other merging unit. So effectively what it does is that any merging unit fails, okay, both your main and backup relays are functional. So you don't have loss in any functionality. So this can be done, okay. So protection can automatically switch over to healthy sample value. So this is one design improvement that we can do. Power quality. So how do we do power quality in digital substation? In PLN, I don't know how it is done. In many other substations, power quality is still with conventional wiring, because there is no method for merging unit. Normally they work on 80 samples per cycle, right? And with 80 samples per cycle, you can monitor up to 10th or 15th harmonic. Now the power quality standards, you need to monitor up to 50th harmonic. This cannot be done with the sampling rate that merging units are doing, but with higher sampling rate like 14 kilohertz, you can monitor power quality. So this is possible, right? Because logically the power quality meter can be driven by sample analog merging unit. So these logical nodes can be put in the field device, and all these logical nodes, they are available. So whatever power quality applications require, those logical nodes are modeled in 61850. It can be possible, right? So this is one more possibility that you can do in digital substation. And with the new standard, that would be 61869-13. So that specifies how the merging unit should behave. So if the merging unit is compliant with -13 standard, and if you have the right profile, you can use that merging unit and your meter for power quality applications. Testing is very important, right? So how we okay, so there are basically two ways of testing. One is conventional, so test from the analog inputs. 5 minutes, okay, I'll finish in 5 minutes. That's the conventional approach, as we do in a conventional substation. So we inject currents and voltages, and if you adopt the same approach, you have to inject currents and voltages in your switch yard, right? The alternate way of testing is remote testing in service without affecting anything. In conventional substation, if you want to test, you have to take shutdown, right? You can't do it when the equipment is live, because it's the protection is still on. Of course, you can make a short circuit of CT, you can run your feeder, and you can disconnect all your wirings, but that's very complicated. I mean, the test links, you can open the test links and inject current and voltage, but think about bus bar protection and all, because it becomes very complicated, right? If your device is involved in a circuit breaker fail, how many test links you will open, you need to be very careful. In digital substation, you can very easily accomplish all this task with test mode and simulation. So it's basically in 61850 edition 2, there are two very important things. One is a test mode and one is a simulation mode. So with combination of test and simulation, basically what we can do is when the substation is running, when your secondary equipment is protecting the feeder, you can still test the function within the relay without taking shutdown, without isolating anything, just by changing the test mode. So because I don't have enough time, so I can't go through all the slides in detail, but generally so simulation mode, what it is that you have your goose messages published from the devices. This is your subscribing device, so it is subscribing to all the goose messages. Now you are connecting your test equipment, which is producing the goose message like this. At this moment your device is not in a simulation mode. The moment you put it in simulation mode, okay, what will happen is that it will start subscribing to the signal given by the test equipment. Okay, so in this case all you need to do is to change the simulation mode. Okay, then also if you test your equipment, how do you check the response, right? For conventional equipment, what I need to do is to I inject current, voltage, whatever, and I check the response of digital output, which is my output relay. Okay, in digital substation what can we do? Because that's my IED, and normally I connect my test equipment on the output and see if it is operated or not. But in 61850 there is a possibility to monitor this point. So this point is op OK, so you can monitor this attribute. So this is how you can accomplish testing. So that's the overall scheme. So you put your protection IED in a simulation mode to begin with. You want to test any function, you put that function in a test mode. When you come to merging unit, you put the merging unit in a test blocked mode so that it does not operate the output actually, but still you will be able to monitor the attribute. So this is how you can perform the testing when you are online. Okay, so network engineering, we need to segregate the traffic appropriately. Otherwise, you have a problem in operation. Configuration, okay, I will not go into detail. Basically, once you build your substation commission, you need to check in all scenarios. So various scenarios of time synchronization, whether your GPS antenna is connected, disconnected, in each situation, how your equipment react. So you need to look at all these aspects. So with that, I end, and happy to take questions. Okay, any questions?
Oke, jika ada pertanyaan, dipersilakan.
Baik.
Jadi kita buka untuk 2 pertanyaan dulu ya.
Terima kasih Sebang. Cek. Thank you Mr. Chirag for the presentation. Mungkin dari hadirin silakan Pak.
Yeah,
Dari
thank you. My name is Alim from head unit of PLN. In your slide presentation, you said that the cost of this digital substation is 10% reduced for
It can be,
protection device.
Yes. Yes.
My question is, can you mention overall cost to build one complete digital substation comparison with conventional substation, overall cost.
Right.
And then my second question is, how to replace conventional substation to become a digital substation? How the method and how long you need time to do it? Thank you.
Right. Yeah, thanks. Okay, so your question was 10% reduction in equipment cost. Okay, so 10% figure that I showed was overall project costing. Now, if you compare just the equipment price between conventional and digital substation, maybe digital substation will have higher price if you compare just the cost of boxes. Because obviously, in conventional substation, you don't have so many switches. In conventional substation, probably you don't need to use GPS clock. In process bus situation, you need to use switches, you need to have additional merging units, you need to have GPS. So purely number of boxes in conventional and in digital, probably digital will have higher cost. But your project is not just number of boxes, right? You need to see if you are able to save money in your project, and this definitely happens. So even though your equipment cost is higher, your other costs like cost to produce drawing, 90% reduction in drawings, right? About 50% reduction in commissioning time. So commissioning time is quite important, right? So you can make all these savings, and therefore in number of projects we have experienced that as a secondary system replacement, you can save around 10, 20, 30% quite easily. And this is what the customers have told us, because for every customer your cost can be different. Some customers, manpower cost, for example in Australia, manpower cost is very high. So if they can reduce number of man days, huge saving. In some countries, maybe the control cable, the cable cost is very high. So, but in general, I think around 10-20% is very reasonable estimation if you look the overall project. The second question is that how long does it take to replace a secondary system? Now this is very open question. It really depends on your shutdown schedules, your cutover schedules, because how you cut over from existing to the new one. But I showed in my example that you can think of the prefabricated building, right? Prefabricated control room, and there you can have the whole secondary system. You can just drop in your existing substation, make all the fiber optic cabling, and then you gradually start cutting over. Yeah.
Okay, I continue my question. So, is it possible that while you're replacing the conventional substation,
yeah,
do not disturbing the operational of substation? Is it possible to do it without disturbing? Thank you.
Yeah, so there are we have refurbishment situation. So you have your conventional substation and you want to move to digital, right? So the substation is secondary system is, let's say, nearly end of the life, and you want to replace your secondary system. So you have two options. Either you replace relay by relay, okay, so replace all the relays, take shutdown of one feeder, replace relay, or let's say you go for digital solution. So you have something similar you will do. So you have sort of cutover stages. So you move feeder by feeder, feeder by feeder. So you can do that, but you need to, stage all these activities properly. I think here also it was done, right, in Indonesia. Yeah. So you have an example of, I don't know, it's Bekasi. Yeah. So this has to be staged properly. Yeah.
Baik. Oke, thank you, Pak.
Okay. Thank you very much.
Thank you so much. Timekeeper masih bisa ada pertanyaan lagi atau kita harus lanjut? Mohon maaf nih. Jadi untuk pertanyaannya kita batasi dulu untuk satu pertanyaan kali ini. Namun kalau ada pertanyaan lebih lanjut bisa kunjungi booth-nya, booth GE, bisa diskusi di sana dengan tim-tim expert dari GE juga dari Guy Group, seperti itu. Mungkin thank you so much Mr. Chirag for the presentation.